Okay, here's questions asking design a voltage divider bias network using a supply voltage 24 voltage and beta is equal to 100 and ICQ is equal to 4 milliampere, VCEQ is equal to 8 voltage, V is equal to VCC divided by 8. And by looking at this, we know this is a BJT transistor because that's the only one has the emitter, collector, and the base kind of thing. So here, ICQ, that's a collector current, and we have the emitter voltage, and we have the collector emitter voltage, that is 8 voltage. So all these are related to the BJT. Okay, and this is the voltage divider. We have to design a voltage divider circuit, and if you remember, voltage divider circuit is basically you will have a supply voltage, that is a VCC. So here when they say supply voltage 24 voltage, that's a VCC. So let's look at the sample diagram, how it's going to look like. So it's going to look like something like this. We're going to have a MOSFET going like this, and it's going to be attached to a resistor, voltage divider, and this one will be also connected to VCC, something like that, and the bottom part will be grounded. Okay, so the circuit is gonna look something similar to this, and here we will have a resistor, 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 resistor. Okay, and this one is R1, R2, and this resistor right here is the RC, and the resistor right here is the RE. Okay, and this one has the IC current, and this one has the IB current, and here this is the IE current, and the current through the first resistor we can call it as I1, current through the second resistor we can call it as I2. Okay, so this is just a sample circuit in order to get some idea about what we are doing. Now we start with the listing given parameters. First we have the supply voltage, that is the VCC. VCC is equal to 24 voltage, and then beta is given to be 100, and then we have the collector current IC is given to be 4 milliampere, and then we have the collector emitter voltage, that is right here. This is collector and the emitter right here, so this voltage is the VCE right here. So that one is given to be 8 voltage, and then voltage at the emitter, that is equal to VCC divided by 8. Okay, so the first thing we can do is, let's call this step 1. Here the IC current provided, we don't know the IB, we don't know the IE, we can find both of them. So first step 1, find IB and also the IE emitter current. We can find both of them. At the same time we can find the VE as well, because that is VCC divided by 8 and VCC is already there, so we can find that one also here. And the relation between IE and IC and IB, because IC is the one provided, if you know the relation between IB and IC, then we can find the IB. IC is nothing but beta times IB. Okay, so from this one we are interested in finding IB, IC available, beta available. So here in this equation, that will give us IB is equal to IC divided by beta, and IC is 4 milliampere. That one divided by beta, that is 100. That is going to be equivalent to 0.4 milliampere, or you can say okay, the question had it 110, but it doesn't matter, You can use 100 or 110, whatever. You have to just divide by that. So if I divide this one by 110, that gives us if it's 100, that is just 0.4 milliamp. Okay, 4 divided by 100, that will be 0.04, or you can say 10 to the power of minus 3 and 10 to the power of 10 to the power of minus 3 is milli. And if you divide this by 100, then that's 10 to the power of minus 2 on top. So that is like 4 times 10 to the power of minus 5 right now. So that is 40, that is equivalent to 40 micro if it's just 100. But here we have 110. If you divide this by 110, that is equivalent to 36.36 microampere. Okay. So that's our IB value. Then the next one is we have to find out the IE. And the relation between IE and the other currents are this. Let me use a different color. IE is addition of other two currents, that is IB and the IC. Because you see, even if you apply KCL, that makes sense, because whatever the currents go here should be the current exiting. Okay, so this there's a current coming through the this one IB. So if I take this node right here, IB is current is entering, IC current is entering, the IE is exiting. So you can say IE is equal to IB plus IC. And we know the IB, that is yeah, we just found out the IB, that is here, right here, 36.36 microampere. 36 micro plus IC current, that is 4 milliampere. 4 milli is 4 times 10 to the power minus 3. If I want to make this one to micro, or I can make this one a milli, that will be easier. This one is equal to 0.036 milliampere. This microampere is equal to 0.036 milliampere, because we have to just divide this one by 1000 in order to make it a milli. So if you do that, then that will be easier. So let's keep it as milli here. This is just 4 milliampere, 4 milli. If you add them together, that's gonna give you 4.036 milliampere. That's our IE current. And the last one we have to find out is the voltage at the emitter. Voltage at the emitter, we have the equation provided in the question, that is VCC over 8. So we can just use that and figure it out. VCC is given to be 24 voltage divided by 8, that is 3 voltage. Okay, now we have found out all of that. The next step is we can find out the resistance, this resistance, this resistance. So let's say that is step 2. Find RC and RE. Okay. For RE, we have the IE available, VE available. So that is straightforward. We can apply Ohm's law. Ohm's law says V is equal to I times R. Therefore, R is equal to V divided by I. So RE should be equal to VE divided by IE. And VE is right here, 3 voltage, divided by the IE that we found out to be 4.036 milliampere. So 4.036 milli right here. and if you divide this one 3/4, that will this milli go, if it goes to the top, that become kilo. So 3000 divided by 4.036, if you divide that, then you will end up getting 743.24 ohm resistance. That's our RE value. Okay, the next one we had to find is RC. In order to find the RC, we can apply KVL around the outside of the transistor. Inside is this, outside is straight line. Like if you go from top to bottom, that's the outside. So if you apply KVL, VCC minus ICRC minus VCE minus IERE should be equal to 0. Okay, that's a KVL. KVL at the output. This is input and this straight line is the output. Let me use a different color. VCC minus ICRC minus VCE minus IERE should be equal to 0. And we have to first make sure we have all these values, otherwise this equation doesn't work. We have to the only unknown variable should be RC, because that's what we are trying to solve. So if it's just one unknown variable, we can solve it, otherwise we have to find something else. So here VCC is known, ICRC we are trying to find RC, IC is known, and VCE is provided in the question, 8 voltage, and IERE is nothing but VE. So instead of IERE, we can just write VE as well. That makes things simpler. So minus VE is equal to 0. Then if I rearrange this equation in terms of RC, I will end up having this equation, VCC minus VCE minus VE divided by the current IC. Plug all the values, 24 minus 8 minus 3 divided by 4 milli, that is equivalent to 3.25 kilo ohm resistance. Okay, that is our RC. Okay, now we found out, we know the VCC, we have the RC value, we have the IC value, we have RE value, IE value, we have the IB value. The only thing that is missing here is we have to find out the R1 and R2 resistance. So in order to find them, we have to just take the inside of the input part of this. Okay, we have to just take this part alone. Here we have VCC, and this one is the R1 right here, and here we have the IB current going through this, and this one is the R2, and that's connected to the ground, and this is the VB voltage right here. Okay, so we have to just consider the input side of this. Okay, so from this one, let's see how we can solve. So when we do the input side of it, there are a few things you have to consider. One of the thing is, for a BJT transistor, the VB is 0.7. Why it's 0.7? Because it's always 0.7 for the silicon transistor. For the germanium it's 0.3, but that's a rare case. In the question, if they don't mention if it's silicon or anything, and if they don't mention VB, we assume it's a silicon, and for silicon VB is 0.7. So we have to just put 0.7 for the VB. And also another thing, that is IB, the current through this is I2, and this one is I1 right here, and the current through this I2, this R2 resistor I2, should be equal to 10 times of IB. Okay, these two things we have to know in order to deal with this one. So first, if you know VB, how is that helpful? Because this is helpful because VB is nothing but VB minus V, and we know the V. If we know VB, then we can find out the VB. VB is gonna be just VBE plus VE, then VB is 0.7, and then VE is what we calculated over here, that's 3 voltage. So VB will become 3.7 voltage. And we can also find out the I2 current. I2 is 10 times IB, then 10 times IB current is known. IB current, that is right here, 36.36 microampere. 36.36 microampere, and if you multiply this one by 10, this is 363.6 microampere. That is the I2 current. Okay, now we have I2 current, we have the VB voltage. We are trying to find out the R2 and R1. So let's say this is step 3. Find R1 and R2. Okay. So if I want to find out R1, I can do it in terms of the relationship between this voltage minus this voltage divided by the resistor in between should be equal to this current. So I can use that over here. Let's try that. So this VCC minus VB divided by the resistor in between, that's R1, should be equal to the current flowing through that, that's I1. Okay, but we don't know the I1. We just found out the I2, but we don't know I1. But if you look at the circuit, if you apply KCL at this node, whatever the current entering should be the current exiting. So I1 should be equal to I2 plus IB, because I1 is entering, I2 and IB are exiting. So I2 plus IB is the I1. So if you know that relationship, then we can apply that one over here instead of I1, because I2 and IB are known already. So we can apply that and find the R1 resistance. So let's do that. So if we rearrange this in terms of R1 resistance, this is going to be R1 is equal to VCC minus VB divided by the current I1. Instead of I1, I'm plugging in the I2 plus IB. So this is going to be VCC minus VB divided by I2 plus IB. And VCC is known, that's 24 voltage, minus VB is also known, that is 3.7 voltage, divided by the I2 plus IB. I2 is known, that's 363.6 microampere. 363.6 microampere, and then plus IB current, that is IB current, let me find out. Okay, that is 36.36 microampere. 36.36 micro. You plug that all in and find the R1 value. That will give you 50.75 kilo ohm resistance. Okay, now we have the R1 value. The next thing is we have to find out the R2. Okay, for the R2, we can do the similar thing. Okay, let's look at this circuit. So okay, VB minus 0 divided by the resistor in between should be equal to I2 current. VB minus 0 divided by the resistor in between should be equal to I2. Therefore, R2 should be equal to VB divided by I2, and the VB is 3.7 divided by I2 that we calculated 363.6 microampere, and that will give us 10.176 kilo ohm resistance, and that's our R1 and R2 values. And that's basically it. These are the things we had to find out. Once we find out, the circuit is complete. Okay, and that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.